Hi there, Haya. This is your lesson for week beginning Monday, the 8th of March, 2021. We're going to move on from refractive index that we looked at last week and talk about interference this week. Now, I mentioned interference a couple of times over the last few weeks, but we're going to get down to the details of what exactly it is and how we calculate it, etc. So, the first thing we're going to do is just a couple of recaps from that 5. The first thing is just some terminology that I'm going to be using quite a lot over the next few slides, and I just want to make sure that we're all 100% with that. The first thing is what exactly is meant by wavelength. So the wavelength is the length of one complete wave, the distance from a point on a wave to where the point repeats itself. So it would be from crest to crest, or from trough to trough, or it would be from a point on a wave to the same point when the wave repeats. So it doesn't necessarily have to be just peak to peak. So we should know that already, but I just want to recap that with you. Wavelength is measured in meters and has the symbol lambda, which is that upside down Y that you should be familiar with as well. The top of the wave is known as the crest, and the bottom of the wave is known as the trough. Try not call it the peak and the trough, it should be the crest. That's the terminology used in the SQA documentation as well. But if you have peak, it's not going to be wrong. The height of the wave is known as the amplitude. The amplitude is the distance from the centre to the crest or the centre to the trough. The higher the amplitude, the more energy, and the amplitude determines the height of the wave. Okay, so that's just a wee bit of National 5 revision. We're going to be using the words crest and trough, wavelength quite a lot over the next few slides. Okay, so this one here just talks about something called phase. Here's another term that we've not really dealt with or talked about before. So waves can have the same frequency, the same wavelength and speed, but still not be the same wave. They might look similar and they might look as if they're the same wave, but they're not exactly the same. And that's because they can be in different parts of their cycle. Waves go up and down, and if a wave is going to the top but the other wave is coming to the bottom, they're not the same wave if they're in a slightly different part of their cycle. So each wave can be in a different part of its cycle, beginning, middle and end, or by any point in between. So if we look at some of these waves at the side, here's the wave here. These two waves at the top are in exactly the same parts of their cycle. As one goes up, the other one goes up. This one here, they're in slightly different parts of the cycle, and these ones are in kind of complete opposite parts of the cycle. One is reaching a peak, sorry, a crest, and the other one is reaching a trough. So that's 3 different ways we can think about waves. And how much they are different from each other in the parts of the cycle they're going through is known as their phase. So to compare where one wave is in the cycle compared to another, we use the word phase. Waves are in phase. This is the top one. If the crests meet the crests and the troughs meet the troughs, and they all align, that's known as in phase, the top one. They are out. I'll do the bottom one first. They are completely out of phase if the crest meets the trough, and in both waves. So crest there meet the trough there meet crest there. That's completely out of phase. And anything in between that's not the top one, not the bottom one, is just known as out of phase. So we've got completely in phase, completely out of phase, and we've got just what in between is just out of phase, and it's not really an in phase wave. Okay, so we then have this thing called phase difference. Now we don't need to know too much detail about phase difference. It's just the fact that if two waves are not in the same part of their cycle, then the difference between a point on one wave to the same point on another is known as their phase difference. So the peak there, the crest there, and the crest there, if the difference between these two crests, although they have the same amplitude, wavelength and wave speed, the difference between the two crests is known as the phase difference. And we're going to go on and talk about phase relationship. So a constant phase difference would be a wave that has a constant distance between peaks on these two waves. This is also known as a constant phase relationship. So this is where we're going to talk about coherent waves. Coherent waves is really important. So a coherent wave, it's important that you know the definition of a coherent wave. It's important we learn this definition at the top. This was asked in the SQA exam a couple of years ago, and a lot of people got it wrong. So coherent waves are waves that have a constant phase relationship, a constant phase difference. So they've always, so here's a diagram here, they've always got the same distance between every point. So the peaks are the same distance apart, and any point on one wave is the same distance to the point on the other wave. So this point here is the same distance between those 2 points as it is between these 2 points. So the blue wave and the red wave have the same distance separating them. They're the same wave, except they're slightly shifted and they're not quite lined up necessarily. So they are known as coherent waves. So a coherent wave has a constant phase relationship. So constant phase relationship means that the phase difference between any point on one wave compared to the same point on the other is the same. The coherent waves will also have the same wavelength, frequency and wave speed, but this is not the definition of coherent. So make sure you don't use that if defining what a coherent wave is. Okay, so interference is basically what happens when two waves come together and they add together. Now, interference is the test for a wave, along with reflection, refraction and diffraction. Diffraction we'll talk about more detail next week, but you may have done a wee bit in that 5. So interference is the test for what makes something a wave, or one of the tests what makes something a wave. If something interferes, then it is a wave, or has wave properties. So interference is a product of two or more waves meeting together. All waves are considered to have a central axis with movement above the axis positive and below the axis negative. So the top diagram here shows you a wave. I put an axis on it, a central axis. Anything above the axis is considered positive. Anything below the axis is considered negative. And when we put two waves together, it's these positive and negative values that combine to give you the resultant wave. So here, I've given you an example here. Here is two waves. They're not coherent. They're completely different wavelengths there, different frequencies, very similar amplitudes, mind you. So you can see there that these two waves, that's got a positive value, and overall there's a positive value there. Here there is a positive value and there's a negative value. But the point is that positive takes away the small bit there, and it's still a little bit positive. Whereas here we've got a negative, makes it negative. So basically just adding up all the values here gives you this value here. This is known as interference. So in all situations, interference is the addition of these positive and negative values to give a resultant wave. Now, the special case we're going to go on and talk about now is if the waves are coherent, we can have what's known as constructive interference and destructive interference, but it only works when the waves are coherent. In other words, constant phase relationship, same wavelength, same frequency, same wave speed, and we're going to show you what these two things mean. So first one is constructive interference. So constructive interference occurs when two coherent waves meet in phase. Here are two coherent waves and they're in phase because their crests meet and their troughs meet. The crest of one wave meet the crest of another, and the product of these two waves produces a double height wave. So I've got the crest of one wave meets the crest of another, but equally the troughs of the waves might meet as well. The product of these two waves produces a double height wave. So here, the amplitude of this wave here is double the amplitude of these two, and this is known as constructive interference. And where this happens, where the waves cross and constructive interference occurs, a point where that happens is known as a maximum. So we're going to go and look at what happens when a wave is coming from this direction and a wave is coming from this direction. If they cross and at that point there is constructive interference, then that's considered a maximum point, or a point of maximum, because you're getting a maximum amplitude at that point. Now, destructive interference is the other type. Only occurs when two coherent waves meet completely out of phase. You'll see here the peaks and the troughs, the crests and the troughs are meeting each wave, and what happens is the positive value here cancels out the negative value, and overall you get 0. So positive value here, negative value here, overall 0. So they cancel each other out, and the product of these two waves produces a 0 amplitude wave. They effectively cancel each other out, and a point where waves cross, so waves come from different directions, if they cross like that, and you would get a point of minimum occurring where you would get destructive interference. Okay, now this is an interference pattern. I'm going to do my best to try and find a video which helps explain this, because this is something we do in class. We do some demonstrations. I would get my class to do a diagram of all this and try and explain it. I'll do my best to try and explain it just now, but hopefully I can get some other videos that will help with this one. So what we have here is two coherent sources. That dot there is a source of waves, that dot there is another source of waves. And these black lines coming out, so this dot here has these black lines coming from it. So as it goes out, there's semicircles coming out from this source. For this dot, you get semicircles coming out from this source. So the dots are the centre of the circles, and each set of circles comes from a different source. What happens is the black lines, so the dots on the bottom represent the origin of each wave source, the curved lines represent the crests of the waves. So these black lines, so if I take this black line here, this black line represents the peak of, or the crest of a wave that's coming from this point here. These black lines represent the crests of waves coming from this point here. And where these black lines cross, you get the peak meeting the peak, which, or the crest meeting the crest, which is constructive interference. So for example, this point here, you've got this line meeting this line, meaning you get a point of constructive interference at that point. Where you have a peak, a crest from one wave meeting the trough of another, that is destructive interference. So for example, if I take this point, say, let's go for here, it's this point here. This point here is halfway between the two black lines coming from this source, but it is on the black line coming from this source, meaning this point here is a point of destructive interference known as a minima point. Now, so the constructive interference points form lines known as maxima lines. So all these constructive interference points line up and form what's known as a line of maxima. There's another line of maxima, another line of maxima. And the destructive interference points line up to make something known as a line of minima. So here is a line of minima, here is a line of minima, line of minima, line of minima. So each line is given a number, which is called its order. This is given the symbol M. Sometimes you notice in old past paper questions it's given the symbol N, but we don't want to get that confused up with the refractive index, so we've called it M. The central line of maxima is known as the zero order maxima down the middle, and every maxima either side of that is given a number, so there is a zero order maxima, a first order maxima, there could be another one, second order, third order, fourth order, all the way around, but we don't have it in this diagram. The first set of minimas from the central one is called the zero order minima, and then that would be the first order minima. Oh, my diagram's wrong, that should have a 1, I'll get that changed. I'll get that changed before on the other one. That should have a 1, that should have a 1 there as well. So first order maxima, first order minima, these should both be 1s. I'll change that in another PowerPoint. And they stretch out on either side. Okay, now this is quite a complicated diagram. We're going to go on, maybe I'll try and explain a bit more detail, but what you would have here is you would have these lines of constructive and destructive interference where these coherent sources here are either crossing over one another, the peaks are meeting the peaks, crests meeting crests, or troughs meeting troughs, or you've got the lines of destructive interference where it's halfway between. Okay, please come on, this is a difficult part of the course, quite hard to explain just over the PowerPoint here. I will find you some extra videos on it as best I can and help explain this. Also, I'd really like you to come onto the class call with your own class or the drop-in on Thursday, and I'll go over it in a bit more detail as much as I can. You can ask me questions about it, but it's quite a difficult thing to do just to talk to you through. Right, how are we going to use this information of all these orders, etc.? Well, we're going to talk about something called path length and path difference, and there'll be some questions in this this week in the booklet. So path length is a distance from the origin of a wave to any point on that wave. So from any point on the wave to, for the origin of the wave, so these two, well, I'll go through the description first. So path difference is the difference between path length to the same point from different sources. So if we have two sources, I know it's a little bit fuzzy, if we have two sources, the path length is simply the measurement from one source to a point, and the path difference would be the difference in length from one source to the point and from the other source to the point. So path length is just the length from where the wave starts to any point. And path difference between two sources is the difference in the length from one point, from the wave to one point, and from another wave to the same point. So for constructive interference maxima lines, the path difference is always a multiple of the wavelength, since the waves must meet in phase. So for all the constructive interference points, and for all the lines of maxima we had an interference diagram, the difference between the path lengths must be a multiple of the wavelength because they are meeting in phase. So this is what this top diagram is trying to show you. So the wave here, the top wave and the bottom wave meet to form a constructive interference point, but they have to be a multiple. The total difference between the two has to be a multiple of the wavelength. They're either meeting exactly at the same point with the same length, or they're one wavelength out, or two wavelengths out, or three wavelengths out, but they must be a multiple of the wavelength out, or constructive interference wouldn't occur. For the bottom diagram here, for points of minima, points of destructive interference, the waves must meet half a wavelength out. Always must be half a wavelength out. So they have to either meet half a wavelength out, or 1.5 wavelengths out, or 2.5 wavelengths out, or 3.5 wavelengths out, and so on and so on. And the number of wavelengths they are out, or number of the multiple which we add on to the half, is the order the order of minima for the second one. So destructive interference minima lines, the path difference is always a multiple plus half the wavelength difference, since the waves must meet completely out of phase. Okay. Now, the questions you're going to have are going to be on these two formulas, and you have your zero order minima in the middle, and then you have zero order maxima, in the middle, and then you've got first order, second order, whatever, going up the way, and for minimas, you will have your zero order minima will be the first one above the zero order maximum. Now, the terminology I know is quite confusing. What I ask you is, please, if you don't do this normally, please do it this week. Keep an eye for extra YouTube videos I've added on to give you further explanation, and please, please, please come on to the class call on a Monday or Thursday, whenever your class call is. I know Mr. Huggins does a different one as well. Come on to your class call, ask questions, and we'll help you through this. Okay? Unfortunately, it's not the easiest thing to teach when you're not sitting in front of us, so we'll do our best, and then you can come on with any questions and see how we get on. Okay, so good luck this week. We're not going to do any more than that this week. And we'll go on and do a wee bit on diffraction next week. Okay? Right, thanks guys. Good luck.